So in the last video, we introduced the concept of metric tensor and talked about its necessity and how it emerges from the concept of dot product. And so what I'd like to do now is to expand this idea, formalize them a little bit more rigorously, yet not so much that it gets out of our range of understanding. So let me first define metric tensor as follows. A metric tensor is a 0 to ranked tensor. So this is the rank of the metric tensor G. I'll explain what does it mean to be the rank of a tensor. So a metric tensor is a 0 to ranked tensor that satisfies three properties. And these are important, yet very, very simple properties. Number one, metric tensor is symmetric in its arguments. It has a very nice consequence that we'll explore within a minute. Number two, a metric tensor is bilinear. Now, here's the fact. A tensor, by its definition, is a linear operation. So everything that is related to tensor is linear. The fact that it is bilinear has something to do with the symmetry and from just the definition of the tensor. Number three, we have positive definiteness. And this is a very important part of the definition for us because sometimes it can get violated without being something that is rather unphysical. So positive definiteness. So now let me go through this definition part by part. First of all, what do I understand by rank 0 to tensor? What it means is that you can think of the metric tensor G as a machine that devours two vectors. Let's say they're A and B. I'm just using the arrow to indicate that they're vectors. If you're not comfortable with the arrow, I'll just use few bars. Notice that I have said nothing about these two vectors, not that they are three-dimensional vectors, although we introduced our metric tensor in both three-dimensional context and we have commented a little bit about its generalization to n dimension. Now, let's just be arbitrary at this stage and consider A and B to be n-dimensional vectors where n is arbitrary. And so what rank 0 to means is that this tensor can devour these two vectors and spit out a number. So this whole object is a number. Let's just say it's a real number. It's also possible to have different sets rather than R, but let's stick to the physical sense. So that's a machine that eats out two vectors and spits out a number. Now, by this definition, you can now imagine the dual vectors. For example, let's say A is a dual vector and it also eats a vector, for example, and spits out a number. And in this case, if A lower bar is the dual vector of A arrow above its head, then this will give us the norm squared of this vector A. But it can be any other vector that it eats up. For example, it can take another vector and spit out a number, and this number will precisely be the dot product of the vector A, whose dual vector is this A, dot B. So if you think it's a little bit difficult to understand, just remember I'm not defining anything new. I'm just reinterpreting the definition of the dual vector. So dual vector in this sense is a rank 0, 1 tensor. What about the vectors? The vectors are also tensors. They're 1, 0 tensors. That means vectors can eat up a dual vector and spits out a number. So if we have, for example, rank m n tensor, that means that tensor can eat m dual vectors, and n vectors, and then it can spit out a number. So if that's a little bit difficult to understand, just rewind this part and you'll see that it's not so difficult concept. What's important is that our metric tensor eats two vectors and spits out a number. What is this number, by the way? This number is actually nothing but the dot product of these two vectors. That's what it is. The metric tensor is simply the generalization of the usual dot product that we had, but it has far greater significance than we used to think. So let me explain these characteristics or definitions. The first one is, of course, the concept of symmetry. What does it mean for a metric tensor to be symmetric? A metric tensor is symmetric in both of its argument. That means if we have two vectors in this order, a first and b second, then it is the same to take b first and then a, and it will give you the dot product of these two vectors. And we know from elementary vector analysis that a dot b is the same as b dot a. This resembles the knowledge that we already have. So that's number one. What is bilinearity? Bilinearity means it's linear in both of its arguments. That's what it says. So if we have G, for example, a comma, then some scalar b into the vector capital B plus some scalar c times some vector capital C, then this is the same as b times g of a comma b plus c times g of a comma c. So notice this is exactly the same way we defined linearity in the linear algebra. The same goes for the first argument too. So G scalar A times vector capital A plus scalar C times vector capital C, comma B is equal to, try to do that by yourself and then see whether you have got it right. So this would be A times G of A, comma B plus C times G of C, comma B. And both of these equations combinedly signifies what bilinearity means. Now the tricky part, positive definiteness. What does it mean? It means that if you have the same vectors a, comma a in both of the spots of the metric tensor, then as long as these vectors are non-zero, then this object, which is a number, should be greater than 0. Sometimes you will see the word positive semi-definite. It simply means that it can be 0, but we will keep it out of this possibility. So this is the formal definition of the metric tensor. This is important for us because later when we'll discuss the geometry of Minkowski's spacetime, we'll modify it a little bit and we'll notice that this one stated here will no longer be valid. Now let us write this in the component form. As we have explained, G A vector B vector should be a number which is a scalar. So in the component form, we can write this number as G mu nu, and then we have A mu B nu, where mu runs from 1 to n, and also nu runs from 1 to n2, and they're contracted, so that means there are two summations, one on mu and one on nu. So if you expand it, you'll see that this is in Euclidean space, or as we say in flat space. This should be a dot b. Then expanding it, we get a1 b1 plus up to an bn. This is also a mu b mu. Notice that mu and mu are contracted as they should by the definition of the dot product. So this will mean a couple of things. One, the matrix representation of this tensor G mu nu, and we pose square bracket around it to indicate that we're writing the matrix representation. This should be, as evident from this expression, a diagonal matrix, and this is simply 1, 1 along the main diagonal and 0 everywhere else. Now, comparing these two expressions, we notice a function of the metric tensor, and that is to lower the index of a vector. So how does it do it? G mu nu times b nu is equal to b mu as the covariant index. So G, the metric, can lower a contravariant index to a covariant index. Now normally the metric tensor G mu nu, especially its matrix representation, is non-singular. If it is singular at some point, then the geometry of that space breaks down at that point. So assuming this to be non-singular, we can find a tensor whose matrix representation is the inverse matrix of this matrix here. We write that matrix like this, G inverse. In the component form, its components are written as G mu nu, both as contravariant index. So since this is inverse, first of all, this should satisfy the following relationship: G mu nu, G nu lambda. This should be simply identity, or the Kronecker delta, which designates the components of an identity tensor. This inverse metric tensor also satisfies this relationship, which we call the raising operation. So we have G mu nu times the vector b nu, and the resultant vector is b mu with a contravariant index. So this is called the raising operation. As you can guess, the matrix representation of the inverse tensor in the Cartesian coordinate system will also be 1 in the diagonal and 0 in the rest of the places. Now at this stage, I should clarify a couple of subtleties. You have noticed that I've changed the indices from ij to G mu nu. So what happens is that whenever we'll denote the space component, right, or the metric of the space, we'll use these ij. In general, we use mu nu when along with space there is also time. So when we denote space time, then we use mu nu. I've used it because of generality, but whenever we talk about 3-dimensional space, 5-dimensional space, or n-dimensional space, we should use ij. Especially, we'll use it for 3D space. And we'll reserve mu nu for 4-dimensional space-time. Another thing I'd like to clarify is that the matrix representation of D is the identity matrix, 1 along the diagonal and 0 everywhere. It's only in the Cartesian coordinate system. If we take, for example, Dij for the polar coordinate system, spherical polar coordinate system, then we would have got 1 r square sine squared theta. In the next section, we'll talk about the transformation of the metric tensor and how does it transform as we change the coordinate system. That means we go from one coordinate system to another.